Okay, so we continue on with our applications of sinusoids, and so we have our first example really set up. We've done the one-link planar robot. Really, that just got us an idea of kind of how the parameters work. But to get the spring mass system, so the spring mass system is governed by the harmonic equation. So whenever we see harmonic, we're thinking sinusoids. So yeah, the harmonic equation, y of t is 2 sine of the quantity 6 pi t plus pi over 2, where y denotes the horizontal component, the horizontal displacement, measured in meters of a mass at time t measured in seconds. And it wants us to determine several different factors. It wants us to determine all of the parameters, the 6 things that we've talked about finding. It wants us to sketch the sinusoid. It wants to define what the horizontal displacement is at a given time of 2 seconds. And it wants us to determine the time required for a mass to reach its maximum negative displacement. So in other words, yeah, as far as it goes in the negative direction. So this is generally the system that we have set up here. So if you think about it, to give you a more solid example, we've got this, maybe I should put it into a wall or something. But yeah, we've got this system set up here, and for whatever reason, it's bouncing back and forth. It stretches out, it crunches in, but it's doing that at a rate that matches the sinusoid wave, that y of t is 2, that the horizontal displacement is 2 sine of 6 pi t plus pi over 2. And this is measured in meters, so it's obviously a much bigger system than what I've got here. So yeah, part A asks us to determine all the parameters. And so if we remember from our previous work that y of t is the amplitude times the sine of the angular frequency, the angular frequency plus the phase angle. So we've already got 3 of our parameters solved for us. And again, we find that to be the case quite often. So we've got that A is 2 meters. We know that omega is 6 pi. And units on that would be radians per second. We know that phi is pi over 2 radians. And those are just given from the equation. We're able to pull out those exactly. And then for the other parts, we need the equation. So for frequency, remember that is equal to omega over 2 pi. So that's 6 pi divided by 2 pi. And so that turns out to be exactly 3 hertz. I guess these are all technically final answers, so we should double underline all of them. We know that the period is just 1 over the frequency. Once we've got that, so it's 1 over 3 hertz. So the frequency is 3 seconds. So it takes 3 seconds for it to bounce, to go from a position all the way out and back in to as close as it can be. And then we know the other one, the phase shift, which is basically how much time relates to this angle shift, is phi divided by omega. And so it's pi over 2 radians divided by omega, which is 6 pi radians per second. And so we end up with 1/12 seconds. All right. And so again, the way we do this, so that's part A. We got all of our 6 parameters. And part B, we want to make a sketch. So remember our rules of making a sketch. Step 1 is really just draw a sinusoid. So I want to start it here. And it doesn't really matter what the numbers are right now, but I know I want to start here, go up, come back down, go down, come back up. And make sure I've got my spacing right. And then I just try to draw a nice smooth curve. So I draw my sinusoid, and then the next part is figuring out where I need to label things. So I know I can label this. I can draw my horizontal axis. I know this is going to be time in seconds. I don't know where I want to put my vertical axis yet. We have to wait and think about those things. But remember that where this starts is negative the phase shift. So that point must be negative 1/12. Which means this point must be the phase shift plus t, or I'm sorry, negative the phase shift plus t, the time it takes to get there. So it's negative 1/12 plus 3. So that is 35/12. Oops, I've got an error in my period. That's why it's not making sense. So it's 1/3. My period is actually 1/3. So this should be 1/12 plus 1/3. So 1/12 plus 1/3, and I get that it is 3/12, which is 1/4. This point, remember, is negative our phase shift plus half our period. So it's negative 1/12 plus, and in general in your homework, you're gonna, if you were writing this out nice and for neatness, you would not try to cram all this information in there. These are just to kind of help us. You want to do this part on scratch paper and just label it here. But since you're not going to see my stretch work, I want to label it on here. So that's 1/3 divided by 2. So that's negative 1/12 plus 1/6, which is 1/12. Yeah, so this time is 1/12. This time is negative our phase shift plus t over 4. So that's negative 1/12 plus 1/3 divided by 4, which is negative 1/12 plus 1/12. So that's 0. So this one actually is going to turn out to be 0, which is also helpful because we know that our phase at 0 we should be at our pi/2 ratings, or that at our max in this case. So you're not going to necessarily be able to see my calculations anymore, but yeah, so we found out that this is the 0, so we can actually draw that in there. And this point here again would be negative the phase shift plus 3/4 of t. So it's negative 1/12 plus 3/4 of 1/3. You got to get really good at doing fractions for this problem. Negative 1/12 plus 3/12. So that's actually 2/12, or again, usually you'll reduce those. So that's 1/6. And again, you should be able to tell that these are equally spaced. That's negative 1/12, 0, positive 1/12, positive 2/12, positive 3/12. It's all there. Okay, so we've got our points labeled. We know we would label our amplitude. We know this amplitude is at 2, and the minimum it goes down to, if I kind of clear out my notes, hopefully you saw those as we were building it, is negative 2. Make sure to tell that this is y measured in meters. That's really, we've got everything on there. And so we can check, always by, if you substitute back in the equation to make sure the answers make sense, that 0, we're at pi over 2. So sine, whoops, I'm off the page, sorry. But yeah, at time equals 0, sine of pi over 2 is 1. So it's at 2, that makes sense. Again, and we can plug in these other parameters to make sure they make sense. Then we're hitting the right spots on our graph. Okay, so that's that part. Part C is probably the easiest part because we wouldn't even have to get into all this mess. Part C just wants us to know that what is y of 2 seconds. So all we have to do, where is it at 2 seconds? So all I have to do is plug that in the original equation. Sine of 6 pi times 2 plus pi over 2. Well, the easy thing to do there is we could just plug that into our calculator. But the other thing we should note on that is that anytime we have a multiple of pi over 2, we can get rid of it. Or, I'm sorry, not 2 pi over 2, but ignore any of 2 pi. Because if you remember from working with our polar coordinates, that we had coterminal angles. So anytime we had 2 pi was just going a full loop around the circle. So whenever we get a 2 pi, we're just back to where we started. So we can actually ignore all this, and we're really just saying, what is 2 sine of pi over 2? And so what we actually turn out with is that y of 2, that sine of pi over 2 is positive 1. So it's actually at 2 meters. So at 2 meters, we find out that it's back at this fully extended point, which again makes sense from our graph if we know that it repeats every third of a second. So if it was here at time 0, at 1/3 of a second, it would be there again. At 2/3 of a second, at 3/3 of a second, it's going to be back there, which is 1. So it cycles 3 times every second, which is the other way of saying our frequency. So in 2 seconds, it's going to cycle 6 times and just bring us back to right where we started. So not surprising that it's at 2 meters once we understand how harmonics work, how these things work. Part D is a little bit different. So it wants to know, when does it reach its negative displacement? And so what are we trying to find? We're trying to find this point down here. Well, from graph, I know that happens at 1/6 second. Because we already figured that out. That when it hits that bottom point, I figured it out earlier. But if I didn't graph it, how would I know that? So what I can do there is basically what I'm trying to find. Min happens when sine equals sine t equals -1. Well, I shouldn't say sine of t. When sine of whatever the stuff is equals -1. And so what that must mean is that, So when does sine equal negative 1? Well, sine equals negative 1, if we do a sine inverse, that happens at sorry, I'm going to try to use the actual words here. So that means sine of 6 pi times t plus pi over 2 has to equal negative 1. How do I get rid of a sine? Well, I do the sine inverse, and we've done that before. 6 pi times t plus pi over 2 has to be sine inverse of negative 1. And I really didn't want to do this, but let's go ahead and slide on to a separate sheet of paper just to kind of finish that out. So if I know that 6 pi t plus pi over 2 is equal to the sine inverse of negative 1. So what angle, if I go back and look at my unit circle, gives me sine is negative 1. So that's if I come all the way around, and my angle is 3 pi over 2. Again, remember, we're doing this in radians, not in degrees, so we need to make sure we do this part in radians. So if you said 270 degrees, you're going to get confused. But we set that, and then we just solve for t. And so 6 pi times t, I subtract pi over 2 from each side, so this side just becomes pi. I divide out, and t is pi over 6 pi, or it's 1/6 second. Which again is good because that's what I got before. Some other things that might happen to you on this. You might, if you just punch that in your calculator and you don't remember, plus pi over 2, your calculator might tell you that this happens at negative pi over 2 is when sine is equal to negative 1. Because it likes to deal with angles, instead of going all the way around to 270 on a unit circle, it likes to just go negative 90 degrees. I can still solve it that way. I would get 6 pi t is equal to negative pi, and I would get that t is equal to negative 1/6 seconds, which is going to be true, so that at negative 1/6 seconds, I'm going to be back. I'll also be at the negative displacement if I kept going back this way. But since we don't generally talk about negative time, I want to find one within the positive axis that hits that. And so what I would want to look at is how do I get back to where I want to be. So add t, the period, until we are in proper range. So negative 1/6 s plus t equals negative 1/6 plus 1/3. That'll give me 1/6 seconds. And so that's where I want to be. And again, if it's depending on phase shifts and those sorts of things, you might find that you have to add more and more. Or you might find that it happens the other way, that even if you use the 3 pi over 2, because of phase shift being very large or something like that, this one could have still come out negative. And we would just have to add the period. Remember t being the period until we get there.